All right, let's take a look at ionic compounds. In the previous video, I took a look at ionic bonds and how ionic bonds are formed. And once these atoms bond to each other, for example, magnesium and chloride, so magnesium bonds with two chlorine atoms forming magnesium chloride, they become an ionic compound. If you don't know how this happens, watch the previous video on ionic bonding first. Let's take a look at ionic compounds now. So ionic bonding was the transfer of electrons from a metal wanting to lose electrons, right? Because metals are in groups 1 and 2, so it's easier for them to get rid of 1 or 2 electrons than receive 6 or 7 electrons, right? And to a non-metal. So the metal donates electrons to the non-metal because the non-metal wants to receive or gain electrons because they're in groups 5, 6, and 7, so it's easier for them to receive electrons than get rid of their many electrons that they already have. So atoms become oppositely charged ions once they become ionic compounds. So for example, with magnesium is a metal, right? So magnesium donates its 2 outermost shell electrons, so it could have a full outer shell. It has a 2+ charge because when you get rid of electrons, you have fewer negative electrons and more positive protons, right? So you're going to gain a positive charge. And these chlorine atoms that receive the negative electrons, they're going to gain a negative charge because the electrons are negative, so they're going to gain a negative charge. So the atoms become oppositely charged ions. Metals become positive since it gives electrons away. Non-metals become negative since it receives new electrons. Now, these oppositely charged ions would be attracted to each other because of electrostatic forces. So electrostatic forces, as I explained in the previous video, it's kind of like magnets. Oppositely charged atoms are attracted to each other, like how the north and south face of a magnet is attracted to each other. So this magnesium and chlorine is attracted to each other because magnesium gains a positive charge and chlorine gains a negative charge. So once an ionic bond is formed, they become ionic compounds because of electrostatic forces that make them attracted to each other since they're oppositely charged together. Okay, that was a lot. And the entire thing of the combination of all the atoms that have ionically bonded together is called an ionic compound. Now, in the previous video, we just did this. We just said magnesium is going to bond to chlorine like this. What I didn't explain is how they form huge scales. So it doesn't just happen in a 2D small scale. This happens on a huge scale. You can notice it's huge because of my huge writings. Okay, so the metals form positive bonds and the non-metals form negative bonds. Because metal becomes positive because it loses, non-metal becomes negative because it receives. And these are attracted to each other, right? So they form huge structures. Plus, minus, plus, minus. So the plus would be all the metals, minus would be all the non-metals. And this doesn't just happen horizontally, it happens vertically too. Plus, minus, plus, minus, plus, minus. Plus, minus, plus, minus. Okay, I'm going to stop here. This is going to take a long time if I want to draw it all. Okay, that's enough. So these form structures like this. And something like this, each positive sign is a metal, and it's a positive ion, and each negative is a negative ion. It's a non-metal. And each ion, as you can see, each of the circle, which are ions, are surrounded on all sides by ions of the opposite charge, because opposite charges attract, right? So they're all electrostatically attracted to each other. So they're making it attracted to everything around it. But this just doesn't just happen in a flat 2-dimensional scale like I've just drawn here or drawn here. This is a bigger scale than this. This got bigger here, right? But it doesn't just happen like this. I'll try and draw something. I suck at drawing, so don't expect some masterpiece. But at least I'll try. Okay, you can kind of see a cube forming, right? Now, each on the cube, there's going to be positive and negatively charged atoms like this. You guys kind of get the idea, right? Positive and negative charged. So this goes to form huge 3-dimensional structures. So not only is it 2-dimensional, it forms huge 3-dimensional structures, kind of like this cube. So imagine it's all filled up with this positive and negative electrons. It forms this huge 3D structure. And it doesn't just happen horizontally, it's also vertically, so it's 3D. Now what we call this, it's a regular lattice structure. This entire 3D structure is called a regular lattice structure. So ionic compounds, which are formed when ionic bonds occur, they don't happen on a small scale like the example we looked at in the previous video. They happen in huge, huge scales. because they're attracted to all the negative and positive atoms around them. So they form huge 3D structures that are called regular lattice structures. This is very important. Now let's take a look at some properties of ionic compounds, which are these regular lattice structures. So ionic compounds have extremely high melting and boiling points. High melting points and boiling points. Why would they have high melting and boiling points? Well, what causes high melting and boiling points? Well, if the bonds are tight, you need lots of energy to break down these tight bonds formed by the ionic bonds, right? And they're strong bonds because they're electrostatically attracted to each other. Attracted, like magnets of the opposite face being attracted to each other. So these oppositely charged metal and non-metal ions are attracted to each other. And this causes a high melting and boiling point because a ton of energy, you need fire to create the energy, right? So you need a lot of energy to break down these tight electrostatic bonds. So that's what causes a high melting and high boiling point. Because lots of energy is needed to break down these strong chemical bonds. And yeah, because they're electrostatically attracted to each other, and meaning there's lots of strong ionic bonds that need to be broken, leading to a high melting and boiling point. Now, one more thing is ionic compounds can conduct electricity. Can conduct electricity. But there's a catch. It can conduct electricity, but the catch is it either has to be melted, so in a molten state, i.e. a liquid. When you're molten, you're liquid, right? So it either has to be a liquid, so in a molten state, or it needs to be dissolved in water. Dissolved in water. So the ionic compound, this 3D structure, the regular lattice structure, needs to be dissolved in water, forming an aqueous solution, which is also written by the acronym AQ. Now, you guys might have forgotten what aqueous solutions are. Aqueous solutions are basically just, it's basically something that's dissolved in water. So where water is the solvent and everything has dissolved within the water, it's an aqueous solution. Aqueous solutions are basically liquids. So aqueous solutions are liquids, but not all liquids are aqueous solutions because not all liquids are dissolved in water. So it needs to be dissolved in water in order to conduct electricity. These are the two catches: molten state and dissolved in water. Either one of these two suffice. It doesn't have to be both. Now, this up to here, it's easy. But what I find really important is you have to try and understand why this happens. Why can't it conduct electricity when it's in its solid state? Why does it have to be in its molten state or dissolved in water? Also kind of molten because they're both liquids, right? So these are both liquids. So in other words, we could say for regular lattice structures, which are ionic compounds, for these ionic compounds to conduct electricity, they need to be liquids. Now, why is that? We're going to explore that in the next video. And I wanted to make another video on this because it doesn't just happen to ionic compounds. I'm also going to explain why nonmetals cannot conduct electricity and why metals can conduct electricity and why, the reason behind why it needs to be molten or dissolved to conduct electricity, where solid metals are able to conduct electricity. That's a really interesting video, and I spent a lot of time researching it, and I found it quite interesting. Because understanding why it happens is really important. It's much better than just memorizing, because it'll stick to your head a long time. And it's quite fascinating. I'll leave a link to that why these ionic compounds can conduct electricity in the next video. But for now, ionic compounds, they occur in a huge scale. I'll just summarize what we just did till now. Positive and negative charge are attracted to each other, electrostatically attracted. And they form huge 3D structures. They're not just small-scale chemical reactions that happen. They happen on a huge scale, 3D scale, forming a regular lattice structure because they're regularly arranged, right? And they form structures, so regular lattice structure, leading to a high melting and boiling point because they're electrostatically, they're ionically bonded together, right? So a lot of energy is required to break down the bonds, leading to higher melting and boiling points. And ionic compounds can conduct electricity if they are molten, so a liquid, or dissolved in water, also liquid, and it's aqueous. Aqueous just means where water is a solvent, so it's dissolved in water. In the next video, I'll look at why this happens and why some metals can conduct and why non-metals cannot.